Next up for us is a topic entitled Work and Energy. Now, this is one of those really interesting topics because energy is something that you've probably talked about an awful lot during your careers at school. However, I would lay odds that you really don't know much about energy at all. If I asked you to describe what energy is to me, I have a feeling you would struggle. And that's okay, because most people would struggle to explain what energy really is. I think a lot of people like the idea that energy is what makes things happen, but hopefully with everything that we've been studying so far, you might actually realise that it's forces that make things happen. It's having unbalanced forces that causes change. So that's probably a better definition for what a force is than a definition for energy. So we're going to investigate this a little bit and then look at how it's a useful idea for us. And in order to do that, we need to make sure that we've got some correct definitions for some key terms that we're going to use. And two terms that are going to get used pretty much interchangeably, really, are work and energy. They are slightly different things, but if you're looking for an equation and you're thinking you need to calculate how much energy is needed to do something, it might be represented as a W for work in the equation. So the sooner you can get the idea that work and energy are very, very closely related into your head, the better. So let's start with our definition for work. So work is the amount of energy transferred by a force acting through a distance. Now hopefully that definition sounds a little bit like it could be an explanation for an equation. And that's because it is. There is an equation that's going to go with that. But that's what we mean by work. It's the amount of energy that's transferred by a force when the force acts through a specific distance. And that's what we mean by work. So it's kind of the amount of energy transferred. And energy, weirdly, has a definition that is the ability to perform work. So if you have energy, then it means that you can use a force to make a change, to cause something to move, for instance. So energy is the ability to perform work. And power, we're going to talk about power a lot more later, but I thought I'd pop it in here whilst we're doing these definitions. Power is the rate at which work is done. So if something has a higher power rating, it means that it can do more work per second. It can transfer more joules of energy per second. So that's something to bear in mind. Now, the big reason why I put power in at this point is because a lot of you are going to get confused. I know this. Before we even get there, before I even see you looking at me with your confused faces, I know it's going to happen. Because you all should know that the unit for power is watts. So if I say that I've got 10 watts, I put 10 and then a capital W. If I have an equation and it has a W in it, like for instance W equals Fs, that W stands for work. It's one of those ones where you've got to remember there's a difference between the symbols and the units. So I'm telling you you'll get confused, so prove me wrong. It's your chance to prove that I am wrong. Don't get confused. But you know, I wager pretty much anything that at least a few of you are going to look at me at some point and have that confusion about what the W's are, whether it's work or whether it's watts. So think about it. Is it a quantity that I'm talking about, or is it a unit that we're talking about? And if so, then what are we relating them to? Okay, at GCSE, you will have had all the types of energy hammered into your brain, right? So kinetic energy, which is energy due to a body's motion, should be familiar. Potential energy, which is energy due to a body's position. The one that you will have come across and that we will use is gravitational potential energy, but that's not the only type of potential energy. Then there's thermal energy, which is energy based on the body's temperature, chemical energy, which is energy associated with chemical reactions, nuclear energy, energy with nuclear reactions, electrical, energy associated with electric charges, and elastic energy, energy stored in an object when it's stretched or compressed. So, we like classifying things. We like to be able to give things names, but the thing is, these are kind of a little excessive. When we really look closely into what's going on with objects and the energy that they have, what we find is that really all types of energy can just be boiled down to being either kinetic energy or potential energy. Now, the big one that I know is going to cause problems in the exam is thermal energy. So if we think about thermal energy, you're used to, I hope, the idea that the hotter an object is, the more thermal energy that it has. And that's fine, that's a very simple way of looking at it. But we're getting to A level now, so we need to start thinking a little bit harder. So what we need to start thinking is, if the object is hotter, what's happening? Why is it hotter? What's going on? What about the molecules is different in a hot object than a cool object? Now, hopefully, somewhere in your minds, you're aware that in a hotter object, the molecules are moving, they're vibrating faster. In a cooler object, they move less, they move slower. So really, that thermal energy is actually just kinetic energy, because it's the molecules having more kinetic energy that when we zoom out, we see that as heat. So thermal energy is really just a type of kinetic energy. So that's something that you might want to keep in mind, particularly for next year when we get into thermal physics and we start looking at nuclear fission and fusion. You may be tempted to talk about thermal energy when really you're going to need to be talking about kinetic energy. So I just want to get that in your minds now so you start thinking about it. It's absolutely fine if you want to talk about these types of energy, but just be aware that these are not hard and fast. Once you get past A level, once you get to degree level, we really don't think about these as being energy. There are people who will argue vehemently with you that electrical energy is a ridiculous concept and that it shouldn't ever be taught. So don't become in love with these. They are things that will change. We are going to talk a lot about kinetic energy and gravitational potential energy in this unit. So those are the main ones that we'll be looking at. Okay. Conservation of energy. Now this is a really important principle. This is one of those fundamental laws of physics. If this wasn't true, the universe would be unimaginably different. So that's how important this law is. What it says is that energy cannot be created or destroyed. All we can do is transfer energy from one type to another. That's what this law says. Can't make extra energy, we can't destroy it. There is a fixed amount of energy in the universe, and all we can do is change it from one type to another. And that's really important. It's so important that I'm actually going to make you draw cartoon strips based on a story all about this, from a story made up by the inimitable Richard Feynman. I will put a copy of the video of him telling the story on your haiku page as well. Just to warn you. You don't have to watch it, but you should give it a look. Richard Feynman, exciting man. Anyhow, energy has to be conserved. Can't create extra. We can't destroy it. We just change it from one to the other. And importantly, energy is a scalar quantity. Energy doesn't have a direction. So all we're doing is changing it from one type to another. We are not, it hasn't got a direction. It's just doing different things. Okay? So, I said we would look at kinetic and gravitational potential energy, so let's have a look at kinetic energy. It is the energy an object has because of its motion and mass, and it has the equation half mv squared. So a half times the mass times the speed squared. Now, this is one of the few equations you are actually going to have to learn because it's not in your data book. This should be something that you are very familiar with, however, so it really should not be a problem. Okay. Now, as a little note, I have used a V here, but I have put speed here. It is because it's the speed, not the velocity. And that's because energy is a scalar quantity, so I can't calculate it using a vector quantity. Now, it doesn't actually matter too much in this instance because it's squared. I'd lose the negative sign anyway if it was a negative velocity. But it is speed because energy is scalar. and the direction has absolutely no relevance to how much energy there is. So that's kinetic energy. Next we've got gravitational potential energy, or GPE, and this is just the energy an object has because of its position in a gravitational field. Weirdly, we don't learn what a gravitational field is until about halfway through next year, so you're just going to have to hang on with that one. But you can basically consider it to be, it's just to do with how far something has been moved from the source of gravity. It's pretty straightforward. If we want to calculate the change in GPE, all we do is mass times gravitational field strength times change in height. So how far we've moved it up or down. This is going to be a weird one, but you can consider, we only ever talk about the change in GPE. So we could consider any point to be zero, a point of zero gravitational potential energy. Then when I lift it up from that position, I'm giving it extra gravitational potential energy. There is no zero. You have to go infinitely far away in order to be able to have zero gravitational potential energy. So that's why we just arbitrarily say, right, for the purpose of this calculation, I'm going to say that the table is zero. When I lift something a metre above, I calculated how much gravitational potential energy it gained by lifting it 1 metre above the table. So don't get fixed to the idea that the ground is zero, because that's something that can cause people to trip up. So just watch for that one. So just symbols, gravitational potential energy is equal to mgh. The deltas just remind you that we're talking about the change in all the time with these. And again, this is one you're going to have to learn. Okay, so work. Work is done when a force moves a point through a distance, so causing energy to be transferred. So I look at the point where I applied the force, I see how far it moved, and I use that to calculate how much work I did in moving it. So work equals force times distance moved in the direction of the force, and that is important, the in the direction of the force. Remember that. So in symbols, that's going to be W equals Fs, and the unit, of course, is joules, because I told you it's the amount of energy transferred, so the energy transferred is in joules. And if energy is scalar, work has to be scalar as well. Okay. Now, I said in the direction of the force, and I highlighted that. The direction matters. But if the direction of the force and the distance that the object moves are not the same, then we have to think about exactly what's going on. So for instance here, I've got an object, and the force I'm interested on is applied in this direction, but the object ends up moving this way because there are other things going on. If I want to work out how much work this force did, I need to take into account only the component of the force that is acting along the direction that the object actually moved. Now, fortunately, you don't have to think about it too hard, because we've got an equation that does all of that for you. All you need to remember is that you use W equals Fs cos theta. So the point of application of the force F moves the distance S cos theta when the object moves through the distance S. Basically, I just look for the component of the force that causes the motion in that direction. I haven't seen many of these questions on the exam, so don't stress out about this too much. Just try and remember that there has to be a component of the force that can act in the direction for it to do any work. The key takeaway from this is that if I apply this force, but it moves at 90 degrees to the direction of the force, that force did no work, because there is no component of the force that acts in that direction. Because if I put cos of 90 in here, that gives me 0, and this all disappears. So that's the most likely scenario you're going to see. Okay, right, nearly there, folks. Last one was short, which is why this one gets to be a little bit longer. Force distance graphs. So I've just said that we can calculate the work done by doing the force times the distance. Well, why not just plot that on a graph? Because if I do, the area under the curve would be equal to the work done. Because the area under the curve would be force times distance, which would give me the area of this rectangle here, and that would also be equal to the work done. So whatever the shape is, I can do it. So the area is still equal to the work. In this case, it would be a half Fs, and the reason that it's a half F is because it would be the average force being applied, which if it started at 0 would just be half of where you end up, assuming it increases linearly, which you can see it does from here. But we don't need to worry too much about that, because we can just remember it's the area under a force distance graph. That makes life easy. Whatever the shape is, if I've got some horrific shape like this one, I can just count the squares underneath it, and that'll tell me what the work is. Easy peasy. So, just to show you an example of how this can be used, if I wanted to calculate the work done by the brakes of a car, if the force exerted varies over the 100 metres as shown in the graph. So I can see it starts at 2 kilonewtons, it goes down to 1 kilonewton after it's gone 50 metres, then it stays at 1 kilonewton for the next 50 as well. So if I want to find the work done, I know the work is equal to the area under the graph. So I'm going to split it into two shapes. I'm going to split it into A and B, and I know that the work is equal to area A plus area B. So that's going to be, for area A, a half times 1 times 50, so a half base times height for area A, plus the 1 kilonewton times 100 to find this one here. And I've just put 1 kilo in here just to show that it's 1,000, because I couldn't bother to write the zeros, basically. But it means the same thing, just need to keep track of it. So that gives me that I have 25,000 plus 100,000, which gives me 125,000 joules. Easy peasy. Right, so that's it for work and energy. Lots of key things to take out from this one. There will be a question on energy on the exam. It's a big topic and it's really important. So we are going to spend quite a lot of time looking at kinetic energy and gravitational potential energy. And we can do all sorts of interesting problems just with these two very simple equations. So, sorry, 3, because we also had work equals force times distance. So with these 3 very simple equations, there are lots of really interesting problems we can solve, and we're going to spend a couple of weeks looking at those now. So remember, I will see you in class, and if you have any questions, just ask when you see me.